Welcome. In this video, we are going to discuss how to work with the probability density curve of normal and standard normal curves, including how to find the proportion of the curve that is either before a certain value, after a certain value, or between two different values. Now, let's begin with a few things to keep in mind. As you look at this probability density curve, which we see graphed below here, we see the probability of various different outcomes, where our outcomes are given on the horizontal axis here. And a key idea to keep in mind is if you look at all possible outcomes, then the total area under the probability curve for all possible outcomes is equivalent to 1. And this corresponds to what we saw earlier. If you remember when we wrote out our probability distributions from an earlier section, we said, okay, if you add up all the possible outcomes, then the total probability is 1. And that's what we're seeing here. Again, this probability density curve is just a different way to represent our probability distribution. Now, one thing that we want to keep in mind, this is a new concept, the area under the probability density curve in some region is equivalent to the probability that if you randomly select an individual from all possibilities, it's equal to the probability that you would select something from that region. So the area under this curve is related to the probability of randomly selecting from that region. So tying this together, since the area under this entire curve is equal to 1, then the probability of all possible events that could occur is equal to 1, which is something we knew from before. So if we start with value A, we go to value B, the area under that curve then has two equivalent interpretations. The first is that the proportion of the population whose values are between A and B, that's equivalent to the area under the curve. And then said in a different way, but same meaning, we have the interpretation we're mostly going to work with, which is it is the probability that if you randomly select an individual or item from the group, it will have a value that lies between A and B. So looking to the diagram that you see below, we can see that between 4 and 6, the area in the curve is shaded and said to be 0.16. So what this means, if you were asked what's the probability if we randomly pick a value between the values 0 and 12, that it would be between 4 and 6, we would say the probability would be 0.16 because that corresponds to the area under the curve for that particular region. Now before we get to our last point, I want to make something clear. This probability distribution gives the probability for different events that were calculated as we calculated probability distributions in a previous section. So for instance, if I was looking at what is the probability in the event of 2 occurring, I would trace up and I would estimate, okay, here's the height of the function at 2 for the probability density. And I would say the probability then of 2 occurring is somewhere between 0.3 and 0.35. Now we need to keep that in mind and keep that idea distinct, because that's just reading the probability density graph from what we're about to talk about next. So the probability of 2 occurring is about maybe 0.33. Okay, we can read that from the graph. But if I randomly select an item, so if I say, what's the probability that if I randomly select a value between all the values given, which in this example is 0 to 12, what's the probability that a single randomly selected item would be 2? That probability is 0. Let me try to untangle that a bit. So in the second case, the case that we're highlighting here, we have a continuous amount of numbers between 0 and 12. We don't just have 12 items. It's not just 0, 1, 2, 3, 4, up to 12. No, it's 0, 0.000001, 0.000012. I can never get close enough to 0, and I can never get close enough to 12. There's actually infinitely many values between 0 and 12 because this is a continuous probability distribution. It takes on all possible values between 0 and 12. So the likelihood, if I'm randomly selecting from the infinitely many different values between 0 and 12, the probability that of those infinite possibilities I select exactly 2, that probability is 0. And we can relate that back to our area understanding, where the probability is the area under the curve. Because if you look just at 2, right now you can see a line on the screen and it has a thickness to it, but that's just so that we can visualize it. If we were actually looking at drawing a line up from 2 from the base up to the height, it would be something of no width. And something of no width can have no area. And if the area is the probability, that's why the probability of obtaining a specific value is equal to 0 if we're picking from all possible values. And that's our explanation of the third point. If you were to randomly select a value between any range, the likelihood that you get a specific value is 0. So let's work with the ideas that we discussed above. We've got our same curve here, so we've got a probability density curve that we've discussed previously. And now we're asked, if a value is chosen at random from this population, what is the probability it will be between 4 and 6? The probability that it will be between 4 and 6 is equal to the area under the density curve from 4 to 6, which we see from the graph above is given to us to be 0.16. So the probability will be 0.16. Now our next question, if a value is chosen at random from this population, what is the probability that it is not between 4 and 6? So not 4 and 6 means everything except 4 and 6. And that's what you can see now highlighted in the graph at the top of the screen. The area that we've highlighted at the top of the screen are the values that are not 4 and 6. Now, if you think about it, we could split up the entire graph into the area between 4 and 6 and the area not between 4 and 6, and that would give you the total area, which from one of our principles in the box given at the top of this page of notes, we know the total area under the curve is equal to 1. So now we can set up an equation that we can solve because we know the area between 4 and 6 is 0.16 plus our unknown area. And we get the equation 0.16 plus unknown equals 1, subtract 0.16 from both sides, and we will get that the area of the curve not between 4 and 6 accounts for 0.84, and then we know the area is equivalent to the probability that if you randomly select an item from the entire group, the probability that it was between 4 and 6 would be 0.84. Let's continue with a similar example. So here we have a probability density curve given. It represents the lifetime in months of a certain type of laptop battery, and we're asked a few questions. If a value is chosen at random from the population, so our population here is from 0 up to 48, what is the probability that we would get a value between 0 and 12? Well, we know the probability of a region is equal to the area under the probability density curve, which here was given to us as 0.35. So the probability is 0.35 since that's the area of this region. Now our next question, if a value is chosen at random from the population, what's the probability it will be less than 18? So if you would think about what values correspond to less than 18, that's from what to what for this graph. So we're interested in values less than 18, but our smallest value on the graph is given as 0, and then up to 18. So here we're looking at this region of this darker blue plus this lighter blue. That entire area under the curve will be the area corresponding to values less than 18. So we take the 0.35 from the first region plus the 0.25 from the second region, and we get a probability of 0.6. Now for the next one, it says if a value is chosen at random for the population, what's the probability it will be greater than 18? Okay, so for our graph given, think what does greater than 18 mean, specifically from what value to what value? Greater than 18 would be this tail of the graph, so that's from 18 to 48. Now as you look at this portion of the graph, we can see unlike the other two portions that gave us the area, we're not given the area here. However, we can take a little bit of information that we know about probability density curves and the information they have given us, and we'll be able to find the missing piece. Would you agree that visually, this entire area under the curve, the first region that you can see me highlighting with my mouse, plus the second region, plus the third region, adds up to the entire graph? Now, what do you know the probability of selecting the entire possibilities is? You know that the probability, or the area under this entire curve, for any value is equal to 1. So we have the equation that the first region's area plus the second region's area plus the unknown region's area must be equal to 1. So now we can do a bit of algebra and solve for the unknown region, which corresponds to the values between 18 and 48. So 0.6 plus unknown equals 1. Subtract 0.6 from both sides. And we get our unknown is equal to 0.4. So always keep in mind that the total area under the curve is 1, and you can often use that to find missing regions if you know all the other values. Now the last one for this is, if a value is chosen at random from this population, what's the probability that it's not between 12 and 18? So we want to exclude the region 12 to 18, everything else is fine. I would encourage you to now pause the video and attempt this question D on your own, and then unpause to check your work. So when they said not between 12 and 18, that tells us the 12 and 18 region's out, so we don't want the 0.25. But that's the only region we're excluding. We're okay with the 0 to 12, which is 0.35. We're okay with the 18 to 48, which is 0.4. So the regions that we're okay with are the 0.35 plus the 0.4, and we'll get 0.75. And this would be what I call the direct way of solving the problem. We're figuring out what do we want, find those probabilities, add them together. An indirect way to solve the problem, which we've seen before in our counting arguments of not and our probability arguments using the word not, is that you can just take the total amount, well, what's the total area under the curve? The total area under the curve is 1, and subtract out the piece that you don't want. What's the piece that we don't want? The 0.25. So if we subtract out the 0.25 from the total, that's excluding the piece we don't want, and we'll be left with the exact same amount as if we calculated it directly. So what you should see here is this is just two equivalent ways of solving the problem. Whichever way makes most sense to you, either the direct way or the indirect way, feel free to solve it based on your preference. So to this point, we weren't necessarily dealing with normal distributions. Instead, we were just dealing with probability distributions and getting our ideas across about, okay, the area under the probability distribution is equivalent to the probability of randomly selecting an item that lies in that region. But now we're going to turn our attention for the rest of the video to normal distributions. Now, normal distributions are specific in that they have exactly one mode. The graph of the normal distribution is bell-shaped and symmetric about the mode. So what that we mean here is, here's our mode, and we can see the graph looks exactly the same, mirror images to the left and the right. The mean, the median are both equal to the mode. So this key idea means that for a normal distributed graph, the mean, median, and mode are all the same. And how can you quickly visually spot the mean, median, and mode that are all the same for a normal distribution? Well, the mode is the center of the normal curve. So we look at the highest point, and this corresponds to our mean, median, and mode for a normal distribution. Now, because a normal distribution has so many nice qualities, it is symmetric, it has this property of the mean, median, and mode, we can actually find very specific behavior for this normal curve. In fact, we can say that 68% of the population will be within one standard deviation of the mean. Now remember, our notation for standard deviation is the sigma. Our notation for the mean is our mu. So here I've got the mean noted here. And can y'all see off to the left we have the statement mu minus sigma. That's the mean minus 1 standard deviation to that point here. And then to the right of the mean is this mu plus sigma. That's the mean plus 1 standard deviation. What this means is this area of the center region, which is 1 standard deviation before and after the mode, accounts for 68% of the total area under the curve. Now the next property that we can read is 95% of the population will be within 2 standard deviations. So the way we would visualize this is now we have our mean. If we go back 1 standard deviation, go back a 2nd standard deviation, we have our mu minus 2 sigma. Similarly, from our mean, if we go forward 1 standard deviation, go forward a 2nd standard deviation, we have our mu plus sigma. Altogether, that accounts for the area we can see shaded here. This entire region accounts for 95% of the entire area under the curve. And then finally, if we take that one more standard deviation out, 99.7% of the population is within 3 standard deviations of the mean. So this is called the empirical rule for normal distributions, and keep these percentages and standard deviation distances in mind. So 1 standard deviation on both sides of the mean has 68%, 2 standard deviations on both sides of the mean has 95%, 3 standard deviations on both sides has 99.7%. Now here we're briefly going to talk about something called the standard normal distribution. And while we introduce this idea here, it will be the main topic of discussion in our next section of notes. So it's introduced here and then fleshed out further in the next video. A standard normal distribution is a particular type of normal distribution. So if you think about it, you've got all the normal distributions, and within that is a subset of normal distributions that have an additional characteristic. What makes a standard normal distribution standard normal is that it has a mean of 0 and a standard deviation of 1. So it's already a normal distribution, but on top of that, the mean is 0 and the standard deviation is 1. If we have that property, it is normal with the mean of 0 and standard deviation of 1. We call it standard normal, and we have something called the z-score. Now the z-score should be seen as something which is the location on the horizontal axis. So the z-score will come from values on the horizontal axis of our probability distribution. Now we know that if I have my normal distribution that is in fact a standard normal, the peak of the graph corresponds to the mean, but the mean is known to be 0. So my z-scores will come from this horizontal axis, but on the horizontal axis, what's left to 0 is negative numbers. And that's why we know in a standard normal distribution, z-scores to the left of the mode are negative. Similarly, if you go to the right of 0, those are positive numbers, so in a standard normal, z-scores to the right are positive. So why are we bringing up the standard normal distribution right now? We need to introduce it because we're going to deal exclusively with standard normal distributions in this video. And then in the next video, we'll talk about how to go from regularly normal distributions and then transform them into standard normal. So in this video, we're going to say, let's suppose we've just been given standard normal distributions. And the reason that we care about that is standard normal distributions are so well understood and well behaved that we actually have a table of values that I'm going to scroll through here briefly, and then we'll come back and explain what it means. This table of values is called the cumulative normal distribution. It is available on our course page from this week. I encourage you to print it out. And it's also in this packet of notes included. So what this does is it tells you for a given z-score, the area to the left of the z-score, and that's what you see traced out here at the top. And then it gives us a variety of values. So all of these middle scores are areas, all the side things are z-scores. We'll talk about how to read it in 1 second. And we've got this chart for positive and negative values of z. Now this chart is extremely important for all of our future problems. I encourage you to print this out. If you only print out a few things for the course, make sure this is one of them. You don't want to just be looking at a digital copy. So let's go through an example to talk about how we would read this chart and then make sense of what we find. So you can see up here I've written, let's find the area to the left of the z-score negative 2.47. Now the whole number, and then the first decimal to the right will be found from this vertical section. So we look down from the list, negative 3.7, negative 3.6, and we find negative 2.4 in this line here. Now in order to verify that we want negative 2.47, that comes from this upper section. Do you see how across in both directions it says z-score here, z-score here? But the vertical section is the whole number and the first decimal place after it. And then the horizontal section is the second decimal place to the right. So since we care about 0.7, we're interested in this, 0.007, because negative 2.47 is what we're looking for. The way we would align these two is, especially if this is printed out, you can maybe get a ruler or a piece of paper to highlight everything in the column for negative 2.4, and then highlight that we want the second decimal place to be 7, where both of these align is the corresponding area for negative 2.47. If I was to draw a quick sketch of the situation, here's my standard normal curve. I've marked my negative 2.47. Far to the left, it's negative, so it should be to the left of the peak in the standard normal. And then we found the area from the portion from the beginning up to negative 2.47. That corresponds to, from our chart, to be 0.0068. So the benefit of this chart is that the area calculations have already been done for you for a standard normal curve. All you have to do is correctly read the chart. Let's practice this a bit more. So in this next example, we're told the curve we're dealing with is a standard normal curve because that chart only applies to standard normal curves. And we're asked to find this area that has been shaded in the region. So we can see the area here shaded is values less than 1.25. And we want to find the area under the curve up to this point. Now we can't find this area geometrically because it's not a straight line figure. Instead, what we're going to do is we're going to say, well, this is a z-score of 1.25. And now I've brought up the chart on the left side of the screen, our examples on the right. This is going to be small if you're just looking on the screen, so again, I recommend that you print this chart out. And always verify to yourself by looking at the picture at the top of the screen. These areas here are specifically the areas from the beginning up to the z-score. And that's shown in this image. So you're getting the areas to the left of the z-score, which matches exactly what we want to find here. Now my z-score is 1.25. As you read through here, although it might be small to see, all of the z-score values on this portion are negative. So I keep going down the list because I'm looking for 1.25. As I scroll, I get to smaller and smaller, or closer and closer values to 0, but they're still negative, so we keep going to the second part of the list. And now as we see that the list continues, notice the z-score is now clearly shifted to the right of 0 because these are positive z-scores on the second page. They start small, 0.1, 0.2. Now I care about the values 1.25, so I know I look at the whole number and the first digit, that's 1.2. 1.2 is here, and then I care about it following up with a 5, so then we go to 0.05 here. So I'm going to align both of these. Okay. Where do the 1.2 row and the 0.05 column intersect? They intersect here, and that value is 0.8944. And that's our answer from this one. So to find values to the left of the z-score, it's merely correctly reading the table. That's all there is to it. Now in our next example, let me zoom out briefly. Looking at the example that we did above, A, and the example that we're about to do, B, below, what do you notice is a clear visual difference between these two in terms of the shaded area? Do you see that in A, the area shaded was to the left of the z-score, which aligns perfectly with the chart because it is giving area to the left. Whereas in part B, we're instead looking at the area to the right, which is not given in the chart. In fact, if I look up a z-score for 0.36, which we can do here, here I've highlighted the 0.3 row. Now let's align that with the 0.6 column. And we get the z-score 0.36 corresponds to an area of 0.6406, but that would actually give me the area, which I've now shaded here in red. So the area to the left of 0.36 is 0.6406, but that's not what we're interested in. In fact, we're interested in the area to the right. Now taken together, even though we don't know what the area to the right is, would you agree the area to the left plus the area to the right is the whole thing? Do you know what the area of the entire probability distribution has to be equal to? The area to the left plus the area to the right must be equal to 1 because together they're the whole distribution. This is a key thing you must remember. The entire distribution's area and thus its probability is 1. So the unknown piece that we're looking for plus the 0.6406 equals 1. Thus we can find the unknown piece by subtracting from both sides. And when we do, we will find that this is exactly equal to 0.3594. So keep in mind that you can find areas to the right of z-scores using the chart, but you must do so in an indirect way. You first directly use the chart to find the areas to the left. Now that's not what you're looking for, but you can use that by subtracting it from 1, the total, to get the unknown area from the right. So every time you approach these problems, make it clear in your mind, are you finding the area to the left of the z-score? If so, that's a direct use of the chart. If it's the area to the right of the z-score, you can use the chart to find the area to the left, but then you have to subtract that from 1 to get the corresponding area from the right. Next, let's look at this next example, our one from part C. Here we see that we've been asked to find the area in this region here, which could be described as the area between z-score negative 0.71 and between z-score 1.62. So whenever you're finding the z-scores between two values, keep in mind the chart only tells you values to the left. So for instance, if I look up 1.62 in the z-score chart, and actually we've had a little bit of practice using this, I would encourage you to pause the video now and using the chart, find the area that corresponds to the area to the left of 1.62. Unpause to check your work. So for the z-score of 1.62, I'm first going to find the row 1.6. And then I'm going to find the column 0.02. I look where these two intersect and I see the value 0.9474. So the total area under the curve up to 1.62 is 0.9474. But if I just trace that over our original graph, do you see that's much too much? That is an overestimate because our original graph did not want all of this area up to 1.62. It wanted from negative 0.7 up to 1.62. So specifically, how much too much is it? It's exactly the area before the negative 0.71 too much. So if we find this area, the exact amount we don't want, we can subtract that from our overestimate and we'll be left exactly with this portion in the middle. So now let's find the z-score of negative 0.71 in the chart and then find the corresponding area. Again, I recommend you pause the video, find it in your own chart, unpause to check your work. So as this is a negative number, I'm currently on the positive part of the chart, so I'm going to have to scroll back. Here we've got the negative portion of the chart, so it's negative 0.71. I'm going to look for the row of negative 0.7. Okay. And I've highlighted all the values that start with negative 0.7. Now specifically I want negative 0.71. We find that by finding the 0.01 column. And where these both intersect, that's our exact value. So for negative 0.01 z-score, so we found the area to the left of negative 0.71 is 0.2389 from the chart. We know the area to the left of 1.62 is 0.9474. And specifically, if we want to find the region between negative 0.71 to 1.62, we're going to take the overestimate of 0.9474 and subtract exactly the portion that we wanted to exclude, which is the tail before negative 0.71, which happens to be 0.2389. Subtracting these two will get the area between these two values is 0.7085. So when you're asked to find the area between two values, find the area for the farthest one first, the largest, find the area before the smallest one, and then take the larger area minus the smaller. Now take a moment to look at our next example. We care about the area shaded, so that's the area to the left of 0.28, and then plus the area to the right of 0.94. Although we haven't done a problem exactly like this before, I think you have the skills needed to think for yourself, how would you find this using our charts that we've been using previously? So how do you find these two separate areas and calculate it? Take a moment to pause and attempt on your own, and then unpause and we'll work through it together. So if I was working through this problem, the first thing that I would notice is this area to the left. That's the best setup we could hope for. The chart specifically gives you area to the left. So I could quickly find this area by looking at negative 0.28 as a z-score and finding its area. I look at negative 0.2 first. So I have to scroll down, got to get closer to 0. Highlight that row. And then we find the corresponding column for 0.08. That helps us find the value specifically for negative 2.8. And that is an area of 38.97. Now that's only part of it. We found the first portion that we're interested in. In order to find the second portion, 0.94, we see that's the area to the right. Now, the chart will only give you area to the left. So if you looked up the z-score for 0.94, we see the corresponding area is 0.8264. Now this is not what we're actually looking for. What we're actually looking for is the value to the right. But we know the value to the left of 0.94 plus the value to the right of 0.94 is the total area, which we know is 1. So we can quickly, from algebra, find this missing piece. Solve to find the unknown by subtracting 0.864 from both sides. And we get the unknown value is equal to 0.1736. Now we found both the areas separately. We wanted the total area, so our final part will be to add these two together. Let's take the 0.1736, add that to the 0.3897, and we get a total area of 0.5633. Now what we tried to highlight in these last four examples, these ideas of how to use the chart to find areas to the left, right, in between of portions in the standard normal curve has been just written down in words here. If you're asked to find areas to the left of a z-score, that's the easiest possible question we could get because it is just directly from the chart. If you're asked instead to find area to the right of the z-score, we can still do so, but we're going to not take the chart's value directly. Instead, we must find that value and subtract it from 1 because we're getting the other portion. Because the chart automatically gives you the value to the left, so by subtracting that value from 1, you get the value to the right. Finally, if you're finding the area between two z-scores, so you're looking from A to B, for instance, you would find the area corresponding to the area to the left of B, then find the area corresponding to the left of A, and then take the larger of those minus the smaller. And these are our 3 strategies. So before you move forward, let's do a quick check. 1, do you understand how to read the chart? If not, go back, print off the chart if it's not already printed, and take some time to understand how you use the vertical axis to find the general area, and then the horizontal axis specifically because it gives the second decimal place helps you find that exact z-score, the area that aligns between the horizontal row that you're interested in and the vertical row that you're interested in. That specific value gives you the area to the left. Okay, so do you know how to read the chart first? If not, review that. Next, after you understand how to read the chart, try to make sense of these 3 different scenarios, and we saw them in our previous example. Keep in mind the chart gives directly the area to the left, so if it's to find the area to the left of the z-score, we can just read the chart. If we need to find the area to the right of the z-score, the chart, while it will help us, does not give us a direct answer. Instead, we have to keep in mind that the area to the left plus the area to the right is 1 in total. So we'll take 1 minus the piece we don't want, and we'll get the area to the right, which is what we're looking for. And then finally, for the area between 2 scores, if you just go to the chart, again, it doesn't give you from here to here. It only gives you area to the left. So if we first find the area to the left of the larger value, that overestimates it. Now, how much does it overestimate it? Exactly by the area to the left of the smaller value. So you find that in the chart. So then you take the overestimate minus however much you overestimated by, and you'll get the exact portion you're looking for. Let's work through this next example. Here it says find the area under the standard normal curve to the left of z equals 0.53. What we need to keep in mind is this is no different than our previous examples, except our previous examples gave us a picture description of this, where here we're getting a verbal description. So my first hint to you is to turn the verbal into a picture. Let's draw our standard normal curve and label where a z-score of 0.53 would be approximately. As you draw your standard normal curve, try to make it symmetric and bell-shaped as much as you can. Then draw your horizontal axis. And now keep in mind that at the peak, since it's a standard normal curve, this is the mean, median, and mode, it's 0. So if we have a positive value, 0.53, I need to be slightly to the right of that. So I'll mark that to the right, 0.53. And they asked for the area to the left. So what I'm looking for is what's shaded here. And since it's area to the left, that's directly from the chart. So here, what will be given in the chart for the area under 0.53 is exactly what we need to find. So let's bring up the chart. Okay. The first part of my chart is negative values, so I'm going to scroll down to the positive portion. You can see now the z-score is firmly after the 0, so this is the positive portion. Okay, we're going to look at where the 0.5 and the 0.03 align. So I find the 0.5 row, I find the 0.3 column, I see they align at 0.7019. And that's all there is to answer this question. Now for the next example, I encourage you to pause the video right now and attempt this all on your own. Read through it, translate it into a picture what you're looking for, using the chart. Figure out what the chart gives you. If that's exactly what you're looking for, great. If not, how can you make that work to find what you're actually looking for? And unpause to check your work, and we'll work through the problem together. So as I read through this, it says find the area under the standard normal curve. Again, they're telling me you're dealing with a standard normal curve. That means I can use the chart. and it said to the right of this z-score. Now I'm going to be very cautious here because I know the chart gives me the area to the left. They're asking for the area to the right, so I need to find the area to the left and then subtract that from 1. So I'm mentally talking myself through that at first. Now let's draw our standard normal bell curve and label where negative 0.13 would be as a z-score. We know the highest point of the standard normal curve occurs where the z-score is 0. So that's my z-score of 0. So I'm going to be looking for values that are negative. So that's to the left, negative 1.3. So maybe somewhere here. And I know the chart will tell me the value to the left. Now, while that's not what I'm looking for, it will help me find the value to the right. So we zoom out to our chart, negative 1.3. I need to go back to the negative portion. I'm going to highlight negative 1.3 and then find where the column intersects with 0.00. And that will give me an area of 0.0968. Now that we have this, we can find the area that we're actually interested in, which is the area to the right, because we know that unknown area plus the known will be equal to 1, the total area. So 0.0968 plus our unknown has to be equal to 1. Subtract the 0.968 from both sides, and we get that our unknown area that we are looking for is equal to 9032. So next up, find the area under the standard normal curve between negative 2.3 and 1.08. We've done a problem like this before. I encourage you to pause, attempt it on your own, and then unpause to check your work. So here I know I need to translate the verbal sentence into a picture so I can visualize what's going on here. It says the area between negative 2.3 and 1.08, so I'll label my negative 2.3. Z-score, 2.30, 1.08, and I'm going to shade the region I'm interested in. Now I know the table does not directly give me area between. Instead, it could give me all the area before 1.08, which is an overestimate, but then I could find the area before negative 2.3, the exact amount it's an overestimate by, and then subtract the bigger from the smaller, and that's what we'll do here. Now this isn't absolutely necessary, but on these ones, I personally prefer to draw a little bit of scratch work off to the side so I could clearly see, okay, this will be the area before 1.08. This will be the area before negative 2.3. Once I have those labeled, I know I can just subtract the larger from the smaller, or the smaller from the larger. Okay. Now looking to the chart, we see the area to the left of negative 2.30 is 0.0107. And then the area to the right of, to the left of 1.08 is 0.8599. And then we know we can take the larger value, subtract that from the smaller value, and that will get us exactly this area in the middle that we're looking for. Now that will be when we subtract 0.8492. Now let's read through this next example. Find the z-score for which the area to the left is 0.93. If you would, pause the video now and go back to some of our previous examples and compare the wording. What is different here? So pause the video, look back at our last examples, and compare it to this one. The difference is, in all of the previous examples, you were given the z-scores and asked to find the area. So notice the order. Previously, you're given the z-score and you're asked to find the area, and when that occurs, it's just a direct use of the chart, as we saw here, right? Because here I can find the z-score specifically, and then the interior of the chart is the areas. But now in these next examples, you're instead given the area and asked to find the z-score. So here the information we've been given is the area, and from that area we need to find the correct z-score. We're reversing the process. Now as we work through problems, I always encourage you to have a visual understanding if possible of what's going on, so let's draw what we've been given. We know the area to the left of some value is 0.93. Now I'm just going to bring up the chart really quick and figure out, is an area of 0.93, is that a positive z-score or a negative z-score? So then I'll know whether I should draw to the left or the right of the mode at 0. Now here I'm focusing on the areas. These are all areas less than 0.04, so I'm going to keep going, scroll. Again, we're looking for an area of 0.93. Even at the largest value on the first page, we get a value of 0.5. Now we're looking for an area of 0.93, so that tells us we're clearly in the positive z range. Now that was just from looking at the chart, but actually we could intuitively know this. See that at the exact middle point, we've split our curve in half. We know the total area is 1, so the area to the left is 0.5, the area to the right of 0 is 0.5. So if we're looking at 0.93, we're going to be clearly quite a bit to the right. So that's a faster approach instead of just looking at the table. So there's some z-score that we don't know, but what we do know is the entire area to the left of it adds up to be 0.93. Now that we can visualize this, we're just going to look through the chart and figure out which z-score gets me closest to an area of 0.93. Looking to the chart, close to 0.0 is going to be about 0.5, so I'm going to get closer because the whole chart is 1. 0.93 is pretty close to the end. So we look around here, I see 0.91. I'm going to keep looking. Here's 0.9332. Let's see if we can get closer to that. 0.931 is closer. I'll zoom in here. Okay, we've got a few candidates. 0.9292 is before. 0.9306. The 0.9319 is now out of the running. And we've just got to determine which of these is closer. So the 0.9292, that's about 0.008 away. Whereas the 0.9306 is only 0.006 away. 0006 away. So this one is closer by a bit. So you're going to choose the closest estimate, whether that's above or below. This is closer to 0.93 exactly. And now we're going to zoom out and figure out exactly what z-score does this correspond to. So to find which z-score this corresponds to, I again make my row and column that intersects to create this score. And we can see the 1.4 row intersects with the 0.008 column, so that's a z-score of 1.48. And that's the closest that we can get to 0.93. So take a moment to think about how we did this example. First, we realized it was somewhat reversed from what we're used to. We're usually given a z-score and asked to find some area. That's basically just working directly with how the chart's set up. However, here we were given the area and asked to find the z-score. That's reversing the process. So in all the areas, we looked and got as close as we could. Remember, you want to get as close to the value that you're looking for, whether that's a little above or below. And then once you find that closest approximation, you see which row and column did it come from. That's the z-score it came from. Now in this next example, it says find the z-score for which the area to the right is 0.84. So again, we're given area and asked to find z-score. We recognize the context clues from this problem. We are being asked to reverse the process. But before we get started, as we did before, I'm going to carefully highlight that it said area to the right. So let's draw what we've been given. The area to the right of the number is 0.84. Now the whole area is 1. So I have to pick a value that's so far to the left that the area to the right of it accounts to 0.84 because the area to the right is 0.84. Now, before we go to the chart, we know the chart only gives us area to the left. It only gives us area to the left. So this 0.84 is not going to be helpful immediately in the chart. Instead, we've got to translate that and say, well, you could tell me the area to the right is 0.84, but then I could tell you the area to the left is 1 minus 0.84, which is 0.16. So now that we've translated this into a helpful area to the left, let's go to our chart. We're going to try to find a z-score as close to 0.16 as possible. Now, we've done an example like this before, so as an opportunity to test yourself, I encourage you to pause the video now, attempt this on your own, unpause to check your work. Now, an area of 0.16, that's definitely before the 0, so we're looking at negative z-scores, so I'm going to go to the negative portion of the chart. And then 0.16 is pretty small, so we're going to get close. Let's see if I can get close to maybe 0.1. So I've zoomed into a region where we're closer to 0.16. So here I can see I'm 0.12, here I'm 0.14, 0.17. Okay, 0.16, let's see again. We're trying to get as close to 0.16 as possible. So it's not the first thing that's close, it's the closest thing. So we'll keep finding closer and closer values. Okay, looking through all the area values, I think our two closest is the 0.15 that you can see to the left and the 0.1611 that you see to the right. Now 0.51587 is actually 0.0013 away, whereas the 0.1611 is only 0.0011 away. So in fact, this is the closest value we can get. Now once we've found the absolute closest value, we're going to zoom out of the chart and we're going to see what row and column does that align with. So this aligns with the negative 0.9 row and the 0.009 column. So that will give me a z-score of negative 0.99. As always, if you have questions, don't hesitate to reach out via our campus communication.